In video number 19, we analyzed the stationary Gaussian wave particle, and now we have to do the same problem but for the traveling Gaussian wave packet. Our wave function psi of x comma 0 is given by a times e to the minus a times x squared, and we have this new extra term right now. In video number 19 we didn't have this term, this is the new term, and here L is a real constant. So the first thing we need to do is we need to find the normalization constant for psi, and then we need to find the psi in terms of position and time. Then we need to find C here, we need to find the probability density, and finally D, we need to find the expectation value of position, the expectation value of momentum, the expectation value of x squared and p squared, and then we have to find the error in x and the error in y. And then we need, after that, we need to check to see if the uncertainty principles is satisfied. So first let's do A, and A is as before in video number 19. So it's going to be the same normalization constant, 2a divided by pi to the 1/4 power. So it's the 4th root of that. So now we need to find the wave function in terms of position and time. If you can recall the Fourier transformation from before, we have phi of k equals to 1 divided by square root of 2 pi. Remember this formula here? The integral from negative infinity to positive infinity of our wave function, comma 0, times e to the minus I k x dx. So let's use that. So now we have phi of k is equal to 1 divided by square root of 2 pi times our normalization constants, 2a divided by pi to the 1/4 times the integral from negative infinity to positive infinity of our wave function, which is e to the minus ax squared times e to the I lx times e to the minus I kx dx, right? So now let's evaluate this integral and do some algebra. I recommend you do this on your own if you have time. Divide by square root of 2 pi times 1 divided by 2 pi a to the 1/4 times e to the minus L squared over 4a times the square root of pi divided by 1 divided by 4a plus I times h bar times t divided by 2m. All of this is underneath the square root times e to some power here. Let's put the power here. So this bracket is the same as I times x plus L divided by 2a, and that is square divided by 4 times 1 over 4a plus I h bar times t divided by m. Alright, close parentheses. So this is the bracket here, okay. Alright, let me see if I did it right. Looks okay. So now let's simplify this a little bit further. So we have the wave function finally, psi of x comma t is equal to 2a divided by h divided by pi to the 1/4 times 1 divided by square root of 1 plus 2I h bar times a times t divided by m times e to the minus to the minus l square divided by 4a times e to the a times something square, I'll fill it up in a minute, divided by 1 plus 2i a t, h bar times t divided by m, and this something is I times x plus L divided by 2a. There's a lot of algebra steps between this equation and the previous one. So this is our final answer for part B. So now let's do part C. So part C, we need to find the probability density. This is the same as psi star times psi. But before that, let's induce a new variable, theta equals to 2 h bar times a times t divided by m. So now, as before, we have psi star psi equals to the square root of 2a over pi times 1 divided by the square root of 1 plus theta square. Notice theta has no units, right? So that's times e to the minus L square over 2a times e to the a times some term let's try to fill it up here. So the bottom is 1 plus I theta, and this one must be 1 minus I theta, right? And the top here we have ix plus L divided by 2a, and this term is square. Here we have minus ix plus L divided by 2a. This term is also square. Alright, so let's take this bracket here and let's try to expand it. So let's take this guy, try to expand it over here. So what do we have? We have, so this is the bracket here, equals 1 divided by 1 plus theta square, right, times 1 minus I theta times ix plus L divided by 2a, this term is square, plus I plus I theta. Remember cross multiplication, times minus ix plus L divided by 2a. This is also square. Alright, so let's simplify it a little bit further. Again, I may skip a lot of steps between this and that. So now this is going to be equal 1 divided by 1 plus theta square times minus 2x square plus L square divided by 2a square plus 2 theta times xl divided by a. Alright, so let's expand this a little bit further. Okay, so now this is going to be equal to 1 divided by 1 plus theta square times minus 2x square plus 2 times theta times x times L divided by a minus theta square times L square divided by 2a square plus theta square times L square divided by 2a square plus L squared divided by 2a squared. Alright, let's take this and simplify it one more step. So this is going to be equal to minus 2 divided by 1 plus theta squared times x minus theta times L divided by 2 times a. And this term is squared plus L squared divided by 2a squared. I really recommend you do this. You take the time to do the steps between these three lines here. So now let's put everything together. Finally, we have the probability density psi of x comma 0 t is equal to the square root of 2 divided by pi times the square root of a divided by 1 plus theta square times e to the minus L square divided by 2a times e to the minus 2a divided by 1 plus theta square. Remember, this is the term in the bracket, times x minus theta times L divided by 2a. This is square times e to the L square divided by 2a. Let's simplify this a little bit further by inducing one more variable. So psi star psi equals square root of 2 divided by pi times omega times e to the minus 2 omega square times x minus theta L divided by 2a, and this term is square. Here omega is defined as square root of a divided by 1 plus theta square. Alright, so now let's find the expectation value of x. So this is part C. It's worth mentioning here that this result has the same result as before in terms of the shape of the Gaussian wave packet. Only this time the center moves at a constant speed v, so this is the center of the Gaussian, moves at this velocity v equals h bar times L divided by m. Alright, so now let's find the expectation value of x. So that is the integral from minus infinity to infinity of psi star psi times x, so x times psi star psi, of course dx. So let's induce a new variable y, which is x minus this v here times time, and if we solve for x we get x equal, of course, y plus vt, right? Alright, so with this new variable we have our expectation value equals to the integral from negative infinity to infinity of y plus vt, that is the x, times the square root of 2 divided by pi times omega times e to the minus 2 omega square y square dy. And if you evaluate this integral, you get the velocity times time. Of course, the first integral is 0, okay, and the second one must be 1 by normalization. So the expectation value of x is equal to h bar times L divided by m. This is the velocity times t. So now the expectation value of p is just the time, the m times the time derivative of the the time derivative of the expectation value of x. And if you do this, you get h bar times L. So now the expectation value of x squared, we're gonna follow the same logic. So this is the integral from minus infinity to infinity of x squared in this case, which is y plus v times t squared times the same wave function. I mean the probability density, which is square root of 2 divided by pi times omega times e to the minus 2 omega square y square dy. So let's go ahead and evaluate this integral here. So this integral is going to have 3 pieces, right, because of this term here. So this term, when you expand it, you get 3 terms anyhow. So now we have the first term is, after you evaluate it, you get minus 1 divided by 4 omega squared plus 0 plus vt square. So now we have the expectation value of x squared is equal to 1 divided by 4 omega squared plus h bar times L times t divided by m, of course, square. Alright, so now let's go to the big piece. The big piece is the expectation value of p squared. This is not as simple as the last one, so you cannot just take the time derivative of this guy here, because again these are operators, right? So we have, let me show you. So this is minus h bar squared times the integral from minus infinity to infinity of psi star, complex conjugates of psi, times the second derivative of psi dx. So now let's look at psi, and let's take one x derivative of psi, and then after that we have to take a second derivative of psi with respect to x, and then we put them together, integrate, and then we get our expectation value of the momentum square. So now let's look at psi. Psi is 2 times a divided by pi to the 1/4 times 1 divided by square root of 1 plus I theta times the expectation, e to the minus L squared divided by 4a, and then we have another exponential to the power of a times ix plus L divided by 2a squared divided by 1 plus I theta. So the psi dx will be equal to 2 times I times a times ix plus L divided by 2a, all of this divided by 1 plus I theta times psi. So the second derivative will be, just take one more derivative of this, so we have 2ia times ix plus L divided by 2a divided by 1 plus I theta, so that's the same thing, times d psi dx, right, plus 2 times I square times a divided by 1 plus I theta times psi. Remember the product rule. So now we have this going to be equal to minus 4a square times I times x plus L divided by 2a square divided by 1 plus I theta square minus 2a divided by 1 plus I theta. Of course, all of this is multiplied by psi. So now let's simplify a little bit further. So this is the second psi derivative with respect to x. So now let's put this into the expectation value of p squared, which gives us 4 times a square h bar square divided by 1 plus I theta square times the integral. Remember, we have to integrate. We still didn't integrate. From minus infinity to infinity of psi, psi star ix plus L divided by 2a square plus 1 plus I theta divided by 2a times the probability density times dx. So let's go back to our y. So in terms of y, we have 4 times a square times h bar square divided by 1 plus I theta square times the integral from negative infinity to positive infinity of minus y plus vt minus I L divided by 2a, of course this is square, plus 1 plus I theta divided by 2a, and this is multiplied by psi star psi dy. So now let's break this integral into two pieces. I think this will be a lot easier. Alright, so let's look at this. So we have this going to be equal to, alright, we have 4 times a square h bar square divided by, that's the same thing, 1 plus I theta square times, let's put curly brackets here, we have minus the integral from minus infinity to infinity of y square psi star psi dy. So that's this first piece here. Remember, because this is squared, so that's the first piece. So now we have the second piece, which is minus 2 times vt minus I times L divided by 2a, that's just a constant, times the integral from minus infinity to infinity of y psi star psi dy, plus, let's open bracket, minus vt minus I times L divided by 2a square plus, of 1 plus I theta divided by 2a, and this is multiplied by the integral from minus infinity to infinity of psi star psi, which should be 1. So dy, and let's close the curly bracket. Alright, so let's simplify this a little bit further so we can understand it. So this is going to be equal to, I recommend to do the steps in between. I'm skipping a lot of steps here. So that's going to be equal to 4 times a square h bar square divided by 1 plus I theta square times curly bracket minus 1 plus theta square divided by 4a minus open brackets of minus I times L divided by 2a times 1 plus I theta, and this term is squared, plus 1 plus I theta divided by 2a, close curly brackets. Let's simplify two more steps. So this is going to be equal to a times h bar square divided by 1 plus I theta times 1 plus I theta times 1 plus L square divided by a, close parentheses, close brackets. And in terms of the original variables we have, this, if you substitute for theta, we get h bar times a plus L square, all of that, just to get to this result. So the expectation value of the square of the momentum is equal to that. So now let's look at the error in x. This is early stuff, right? So now psi of x squared, sigma of x squared equal to the expectation value of x squared minus the expectation value of the square of the expectation value of x. So you do the substitution, you get this to be equal to 1 divided by 4 omega squared. So sigma x is equal to 1 divided by 2 omega. Alright, so now let's do the y. The p, the error in the momentum is equal to the expectation value of p squared minus the square of the expectation value of p, which is equal to, let's do it here. So we have h bar squared times a plus h bar squared times L squared minus h bar squared times L squared, which is equal to h bar squared times a. So finally the error in the momentum is equal to h bar times square root of a. And indeed, if you multiply these two, you will find that the uncertainty principles still satisfies.